Hey everyone, Niraj here. So, I have a question for you. How does your phone know the fastest way to get you home? Or how does Netflix know exactly what show you want to binge next? It feels like magic, right? Well, it's not magic, it's something way cooler. It's algorithms. These are the secret instructions, the hidden blueprints that power so much of our daily lives, from finding a contact in your phone to the undo button that just saved your project. They are the superheroes of the digital world, working silently in the background, making complex problems simple. Today, we're going on an adventure to pull back the curtain on these digital superheroes. We're going to break down the top 10 most important data structures and algorithms, or DSA, that every programmer, engineer, and curious mind should know. But here's the deal. We're not just going to talk about abstract code. We're going to connect each one to a real-life example you already understand. Think of it like a science class, but instead of dissecting a frog, we're dissecting the logic behind Google Maps, your favorite video game, and even a simple deck of cards. So buckle up, because by the end of this video, you're not just going to know what these algorithms are, you're going to see them everywhere. We're going to build your intuition, so the next time you're stuck in traffic and your GPS reroutes you, a little light bulb will go off and you'll know exactly what's happening under the hood. Stick around until the very end, because understanding this stuff is like getting a superpower. You'll start seeing the world in a whole new, more logical way. Let's get into it. Okay, first up is an absolute classic binary search. Now, imagine I hand you this massive, old-school, 1,000-page dictionary, and I tell you to find the word zebra. What do? You're not going to start at aardvark and flip every single page, right? That would be insane. That's what we call a linear search, and it's painfully slow. Your intuition tells you there's a much smarter way to do this. Your brain instinctively performs a binary search. You open the dictionary right to the middle, you land somewhere in the M's. Now you know zebra has to be in the second half of the book. So you completely ignore the first half. You've just eliminated 500 pages in one move. That's the core idea. You take your problem and you chop it in half. Instantly, your problem is 50% smaller. This is a game changer in efficiency. So you take that second half from M to Z and you do the exact same thing again. You split it in the middle, maybe you land on T. Okay, Z comes after T. So now you know it's in the last quarter of the book. You've now eliminated 75% of the entire dictionary in just 2 steps. You can see where this is going. You keep splitting the remaining section in half, over and over, rapidly closing in on your target word. This divide and conquer strategy is incredibly powerful. Instead of checking 1,000 pages one by one, you might only need to check 10 pages. Think about that. 10 checks versus 1,000. That's the difference between finding something in a few seconds versus a few minutes. This is why computers can search through millions of items like your phone's contact list or a massive database at a company like Amazon and give you a result almost instantaneously. The only catch, and it's a big one, is that this trick only works if your data is sorted. Just like you can't use this method on a shuffled deck of cards to find the ace of spades, a computer can't use binary search on an unsorted list. The dictionary works because it's already in alphabetical order. So remember, binary search is your super fast detective, but it needs an organized crime scene to work its magic. Alright, so binary search needs sorted data. But how do we get it sorted in the first place? Let's talk about one of the most elegant ways to do that. Merge sort. Imagine you're a teacher's assistant, and you've just been handed a giant, messy stack of 500 exam papers all jumbled up. Your job is to sort them by student's last name. Staring at this mountain of paper is overwhelming. Where do you even begin? Merge sort tells you to not panic and instead just break the problem down. You take that big pile of 500 papers and you split it in half. Now you have 2 piles of 250. That's still a lot. So what do? You split them again. Now you have 4 piles of 125. You keep doing this over and over. You divide until you're left with 500 individual piles, each with just one single exam paper in it. Now, here's the clever part. A single paper is by definition already sorted, right? There's nothing to organize. So now we start the merge phase. You take 2 of those single paper piles, say Smith and Jones, and you merge them into one correctly sorted pile of 2 Jones, Smith. Easy. Then you take 2 more single piles, say Davis and Brown, and merge them into Brown Davis. You continue this process, merging all the single piles into sorted piles of 2. Once that's done, you take 2 of your sorted 2-paper piles and merge them into a perfectly sorted 4-paper pile. For example, you take your Jones, Smith pile and your Brown, Davis pile. You just compare the top paper of each pile, Jones versus Brown, take the smaller one, Brown, and repeat. The merging step is simple because you know each little pile you're working with is already sorted. You just systematically build up bigger and bigger sorted piles. You repeat this merge and combine step until finally you're merging two big piles of 250 sorted papers back into your final, perfectly sorted stack of 500. This is the beauty of merge sort. It takes a huge chaotic problem, breaks it down into ridiculously simple pieces, solves those simple pieces, and then elegantly combines the solutions back together. It's a reliable and efficient way to bring order to chaos, whether it's exam papers or millions of data points in a computer system. So, merge sort is great, but let's look at another sorting champion, quick sort. It's often even faster in practice. To understand this one, let's switch from papers to books. Imagine you have a long shelf of books, all completely out of order by height, and you want to arrange them from shortest to tallest. Quick sort uses a clever strategy involving a pivot. First, you just pick a book from the shelf at random. It doesn't matter which one. Let's call this our pivot book. Now you go through all the other books on the shelf, one by one. For each book, you make a simple decision. Is it shorter than the pivot book, or is it taller? You create two new piles. All the shorter books go into a pile on the left, and all the taller books go into a pile on the right. After your first pass, you'll have three things: your pile of shorter books, the pivot book itself, and your pile of taller books. Now here's the cool part. You know for a fact that the pivot book is now in its final correct position on the shelf. Everything to its left is smaller, and everything to its right is larger. You've locked one book into place, and more importantly, you've created two smaller, independent sorting problems. So what do you do next? You guessed it. You apply the exact same logic to the two new piles. You go to the shorter books pile, pick a new pivot from within that pile, and partition it into even smaller and taller subpiles. You do the same thing for the taller books pile. You're essentially running quick sort on the left side and quick sort on the right side. This process, called recursion, continues until you're left with piles that are either empty or have only one book, at which point they are, by definition, sorted. Unlike merge sort, which does all the work on the way back up when merging, quick sort does its main work up front during the partitioning step. It's an incredibly fast, in-place sorting algorithm that, with a good choice of pivot, can bring order to a chaotic bookshelf or a massive array of data in a flash. Okay, let's move from sorting to searching, but in a different way. Imagine you're standing at the entrance of a giant hedge maze, and your goal is to find the exit in the fewest possible steps. How would you approach this? This is where breadth first search, or BFS, comes in. It is your ultimate strategy for finding the shortest path between 2 points. BFS works by exploring the maze layer by layer. Think of it like ripples in a pond spreading out from where a stone was dropped. From your starting point, you first look at all the paths that are just one step away. You check every single one of them. If none of them is the exit, you haven't failed. You've just completed the first level of your search. You now know the exit is at least 2 steps away. Now, for the second level, you take all those spots you just visited, the ones 1 step away from the star, and you explore all their unvisited neighbors. You're essentially expanding your search radius by 1 unit in all possible directions simultaneously. You're exploring the maze broadly, hence the name breadth first. You keep doing this level by level. First all paths of length 1, then all paths of length 2, then 3, and so on. The moment you find the exit, you can stop. And here's the guarantee that makes BFS so powerful. Because you explored all the 1-step paths before any 2-step paths, and all 2-step paths before any 3-step paths. The first time you find the exit, you are guaranteed to have found one of the shortest possible routes to it. There can't be a shorter path, because you would have found it on an earlier level of your search. This isn't just for mazes. This is how social networks can suggest people you may know by looking at your friends, level 1, then your friends' friends, level 2. It's also a fundamental principle in networking for finding the quickest way to send a packet of data, and for AI in video games to find the shortest path for a character to walk from point A to point B on a map. BFS is your go-to for finding the quickest, most direct route, 1 level at a time. Now let's contrast BFS with its sibling Depth First Search, or DFS. They sound similar, but their strategies are completely different. If BFS is like ripples in a pond, DFS is like a spelunker exploring a cave system. Imagine you're in a huge, unfamiliar building with many floors and rooms, and your goal is to visit every single room to make sure it's empty. With DFS, you don't explore broadly, you explore deeply. You pick one path and you follow it to its absolute end. Let's say you enter the building and see 3 hallways. Instead of peeking down each one, you commit to the first hallway. You walk all the way down it. You enter the first door you see, and then the first door inside that room. And you keep going deeper and deeper, following one single path. You only backtrack when you hit a dead end. Once you're in a room with no more new doors to open, you step back out into the previous room and see if there were any other doors you skipped. If not, you backtrack again. You only explore that second hallway from the main entrance after you have exhaustively explored every single room, nook and cranny connected to the first hallway. You go deep, then you backtrack, then you go deep again. This strategy might not find the shortest path. In our maze example, DFS might wander down a very long, winding path to the other side of the maze before ever checking a very short path right near the start. So why would we ever use it? Well, DFS is fantastic for problems where you need to know if a path exists at all, or for visiting every single point in a network, like our building inspection example. It's also the basis for solving puzzles like Sudoku, or navigating a decision tree. An AI trying to solve a Sudoku will use DFS to try putting a 1 in a square, then a 1 in the next, and go deep down that path of choices. If it gets stuck, it backtracks and tries a 2 instead. DFS is the tenacious explorer, committed to exhausting one possibility completely before trying another. It's not about finding the shortest path, but about leaving no stone unturned. So, BFS is great for finding the shortest path if every step is equal, like in a simple maze. But real life is more complicated. On a map, the shortest distance isn't always the fastest route. One road might be shorter, but have tons of traffic, while a longer highway is clear. This is where the legendary Dijkstra's algorithm comes in. It's essentially the brain behind Google Maps. Dijkstra's finds the shortest path in a weighted graph, where each path or road has a cost or weight associated with it. In this case, the time it takes to travel. It works by keeping track of the cheapest known way to get from your starting point to every other intersection on the map. Initially, the cost to get anywhere is infinite, except for your starting point, which is 0. The algorithm then starts exploring. It looks at the current location, starting with your home, and examines all the roads leading out of it. It calculates the time to get to the next intersection, like 5 minutes to intersection A, 10 minutes to intersection B. It records these as the current best times. Then, and this is the key, it always moves to the unvisited intersection that is currently cheapest to reach from the start. Let's say intersection A was the cheapest, 5 minutes. The algorithm now moves there and explores its neighbors. Maybe from A you can get to intersection C in 2 more minutes. The total time from home to C via A is 5 plus 2, which is 7 minutes. The algorithm checks, is 7 minutes a better time to get to C than any way we've found so far? If yes, it updates the best time for C to 7 minutes. It systematically and greedily always explores from the cheapest known point. This process continues, always expanding from the lowest cost frontier, constantly updating the quickest known routes to every point on the map until it finally reaches your destination. When it does, it's not just a path, it's the provably fastest route, taking all the traffic, road speeds and distances into account. Every time your GPS says recalculating route, it's likely a version of Dijkstra's hard at work, finding you the new optimal path based on changing conditions. Let's talk about a powerful problem-solving technique that sounds intimidating but is actually super intuitive. Dynamic programming. Imagine you're planning a multi-day road trip from New York to Los Angeles. You have a list of cool cities you could possibly visit along the way, and you want to plan the most scenic route possible. The number of possible combinations of stops is honestly astronomical. So how do you find the absolute best one without, checking every single option? Dynamic programming tackles this by breaking the giant problem down into smaller, simpler subproblems, and then saving the answers so you never have to solve the same problem twice. For our road trip, instead of trying to solve what's the best route from New York to Los Angeles, all at once, you'd start smaller. You'd first calculate the best route from New York to, say, Chicago. Then you'd calculate the best route from New York to St. Louis. Now, When you want to calculate the best route to Denver, you might have a path that goes through Chicago and a path that goes through St. Louis. Here's the magic. You don't need to recalculate the best way to get to Chicago. You've already solved that subproblem and stored the answer. You can just look it up. You reuse your previous work. This is called memoization, remembering the results of computations. The Fibonacci sequence is the classic textbook example. To get the 10th Fibonacci number, you need the 9th and 8th. To get the 9th, you need the 8th and 7th. You can see you'd be recalculating the 8th Fibonacci number multiple times. Dynamic programming says, no, calculate it once, write it down in a table, and just look it up the next time you need it. It trades a little bit of memory space for a massive gain in speed. By working your way across the country, solving for the best route to each intermediate city, and storing that result, you eventually reach Los Angeles. At that point, you can easily determine the overall best path by tracing your steps back through your saved optimal subroutes. Dynamic programming is all about solving complex problems by cleverly solving and remembering the solutions to their simpler parts. It's the ultimate strategy for work smarter, not harder. Okay, let's talk about finding things instantly. We discussed binary search, which is fast, but it requires sorted data. What if you could find any item in a massive collection in a single step without any sorting at all? This is the superpower of hashing. Imagine you're in charge of student records at a huge university with 50,000 students. You need to be able to pull up any student's file in a split second. Your storage system is a giant room of filing cabinets. A linear search would mean starting at the first cabinet and looking through every single file until you find the right one. A nightmare. Hashing is like having a magical index system. It uses a special function called a hash function that takes a piece of information, like a student's ID number, and instantly converts it into a specific location, like cabinet 17, drawer 3. This hash function is a deterministic black box. If you put the same student ID in, it will always spit out the exact same cabinet and drawer number. So, when a new student, let's say Niraj with ID 1138, enrolls, you run his ID through the hash function. It spits out, say, location 525. You go directly to location 525 and place his file there. There's no searching involved. Later, when you need to look up Niraj's file, you don't search the room. You just take his ID 1138, run it through the exact same hash function, which again tells you go to location 525. You walk directly to that spot and boom, there's his file. This is what we call constant time lookup, or O of 1. The time it takes to find the file is the same whether you have 100 students or 100 million students. It's incredibly efficient. Of course, there's a potential problem. What if two different student IDs happen to hash to the same location? This is called a collision, and there are smart ways to handle it, like creating a small list of files at that location. But the core idea remains the same. Hashing is the backbone of databases, caches, and programming language dictionaries or maps. It's the fastest way to organize and retrieve information when you have a unique key, like a username or an ID number. Now for something beautifully simple but incredibly useful, the stack. This data structure has a rule that's easy to remember: last in, first out, or LIFO. The best real-world analogy is a stack of plates at a cafeteria. When a clean plate is added, it's placed on top of the stack. When someone wants a plate, they don't dig to the bottom. They take the one that was most recently added, the one right on top. This last in, first out behavior is exactly what makes the undo feature in any software possible. Think about what you're doing in a text editor or a photo editing program. Every time you perform an action, typing a word, changing a color, resizing an image, the program pushes a record of that action onto a stack. You type another word, and that action gets pushed on top of the previous one. Then, you make a mistake. You hit Ctrl+Z or the undo button. What does the program do? It pops the most recent action off the top of the stack and reverses it. The last thing you did is the first thing to be undone. Hit undo again. It pops the next action off the stack and reverses that one. The stack perfectly remembers the sequence of your operations in reverse order. This same principle is used for the back button in your web browser. Every time you click a link, the address of your previous page is pushed onto a stack. When you hit back, the browser simply pops the last address off the stack and navigates to it. It's a fundamental concept that also governs how computer programs manage function calls. When one function calls another, the system uses a stack to remember where to return to when the second function is finished. So, the stack isn't about complex searching or sorting. It's about managing a sequence of items or tasks in a very specific order. It's a temporary memory that follows a strict LIFO policy. From undoing mistakes to navigating the web, this simple structure is a silent but essential part of your everyday digital interactions, ensuring things can be rolled back in the exact reverse order they were performed. Finally, let's look at the counterpart to the stack, the queue. If a stack is a stack of plates, a queue is simply a line of people. And it follows the rule everyone understands from kindergarten: first in, first out, or FIFO. The first person to get in line is the first person to get a ticket. You don't get to cut in front. Well, you're not supposed to. The order of arrival is the order of service. This data structure is all about fairness and order. In the computing world, queues are everywhere, managing tasks that need to be done sequentially. The most classic example is a print queue. When you and your colleagues all send documents to the same office printer, the printer doesn't just print them randomly. It puts them into a queue. The first document sent is the first one to be printed. This ensures that resources are shared fairly and tasks are processed in a predictable sequence. Imagine you're downloading multiple files at once, or your computer is juggling multiple background processes. The operating system uses queues to manage these tasks, giving each one a slice of CPU time in the order they were requested or based on a priority system. It prevents chaos and ensures everything gets done eventually. Another great example is a customer service chat system. When you message a company for help, you're placed in a queue. The support agents are serving customers in the order they initiated the chat. This ensures that the person who has been waiting the longest gets helped next. It's the digital equivalent of now serving number 57 at the deli counter. The operations are simple. On queue means to add an item to the back of the line, and dequeue means to remove an item from the front. So while the stack was about reversing order, last in, first out, the queue is all about preserving it, first in, first out. It's fundamental for managing shared resources, processing tasks sequentially, and handling any situation where fairness and order of arrival are critical. From your printer to the servers handling your internet traffic, queues are the silent organizers making sure everyone gets their turn. So there you have it. The top 10 foundational algorithms that secretly run the world around you. From sorting your emails with Quicksort, to finding the fastest route with Dijkstra's, to undoing a mistake with a stack, these aren't just abstract computer science concepts. They are elegant solutions to real, everyday problems. Understanding them is like learning the grammar of the digital language. It empowers you to not just use technology, but to understand the logic and ingenuity behind it, turning you from a passive user into a creator who can build amazing things. But watching this video is just the first step. The real learning begins when you start applying these ideas yourself. The next time you're sorting a deck of cards, think about merge sort. When you're looking for a contact in your phone, recognize the speed of binary search or hashing. Try to spot these patterns in the wild. The best way to master these tools is to get your hands dirty, so try to code them up or even just sketch them out on paper when you face a problem that could use them. This is the stuff that separates a good programmer from a great one. But more than that, it's just fascinating. I hope this gave you that aha moment. If it did, and you enjoyed this deep dive, do me a huge favor and hit that like button and subscribe so you don't miss our next engineering adventure. And I'm curious, which one of these was your favorite? Or is there another algorithm you think is super cool? Let me know down in the comments. Thanks for watching, and I'll see you in the next one.